Yeah, just consider to address this read after write hazard and to find the solution. In a given program P, there are four instructions. The sequence of instructions. Instruction 1, add the value R2 and R1, and the result will be stored into R3. That is the first instruction. Second instruction adds the value which is reading from R3 register and R5 register, and the result will be stored back into the R4 register. Yeah, if you carefully observe here, the third instruction is reading the value from R3 register and R5 register and performing the add operation, and the result stored back into 6. Similarly, the fourth instruction, read the source 1 operand value from R3 register, source 2 operand value from the R5 register, and the result stores back into R7 register. So the source operands are also reading from the register file, and the destination, the result will be writing into the destination, that is also into the register file. So here the question, is there any dependencies in this instruction sequence? Can you please address the dependencies? Yeah. So if you recall this one, the instructions 2 is depending upon the instruction 1. Why? Because instruction 2 requires a source 1 operand that reads from R3. So that is the value from the first instruction destination register. Okay, so before executing this instruction, if instruction 2 try to read the value from R3, that may give a different value, that wrong value will be given, right? So if you look at the pipeline for execution, because it is a parallel execution. So in the first cycle, first instruction allowed inside the pipe, and that is instruction fetching stage. So first instruction is fetching from instruction memory. Then in the second cycle, instruction 1 moves into the instruction decode stage in the pipeline. That means reading the R1 and R2 values from register file. So instruction fetching stage become idle. So instruction 2 allowed inside the pipe at cycle 2. And instruction 2 fetching from instruction memory. In the third cycle, instruction 1 moves from instruction decode stage to the instruction execution stage, where the ALU takes the input from R2 register and R1 register to perform the add operation. Then instruction 2 that moves from instruction memory into the instruction decode stage to decode the source operands. So register file is accessing. The source operands are identified like R3 and R5. Okay. So the next one is the instruction 3 will be allowed inside the pipe at cycle 3. That is, instruction 3 is fetching from instruction memory. Okay, so at cycle 3, instruction 1 is busy with the ALU. Instruction 2 is reading the data from register file. Instruction 3 is fetching from instruction memory. So there is no problem here. At cycle 4, instruction 1 moves into the memory access stage. Okay, where the instruction 2 at cycle 4 enters into the execution stage. but it needs the R3 value and R5 value. But R3 is not yet updated. Not yet updated because R3 value only updated at the write back stage. So assume that instruction 2 moved into the execution stage at fourth cycle, instruction 3 moved into instruction decode stage. So instruction 3 also trying to read the value from R3 register. At cycle 4, instruction 5, suppose allowed inside the pipe in instruction fetching stage. So at the third cycle, instruction 2 needs R3 value. At fourth cycle, instruction 3 needs the R3 value, but actually the value is not yet updated in R3 register. So that means at this stage, if instruction 2 and 3 reads the value from R3, they may get wrong value. They will definitely get a wrong value. So the instruction 2 and 3 output will be wrong because the result will be right in R3 at the write back stage. At the fifth cycle, first half, it will write the value into R3. So before that, if any instruction trying to read the value, they will get wrong values. Right? That means in these 4 instructions, 2 and 3 will get wrong values. Whereas the fourth instruction, suppose, move to the instruction decode stage at the fifth cycle. So the instruction 4 read R3 value in the second cycle, second half cycle at fifth stage. So instruction 4 will get the correct value only by that time R3 is updated. So therefore, there is a no data hazard for instruction 4, but there is a data hazard for instruction 2 and instruction 3. There is a data hazard for instruction 2 and instruction 3. If this hazard is not there, then these 4 instructions, they complete their execution in how many cycles? Means if there is no read after write data hazard, these 4 instructions completes their execution in total 8 cycles. Yeah. So what will be the solution? Means the first solution is it needs to stop execution of instruction 2 and instruction 3. That we call stall the pipeline. So first, instruction 2, let us find the solution. Instruction 1 enters into the pipeline in the first cycle in the instruction fetching stage. At the second cycle, instruction 1 move into the instruction decode stage, and instruction 2 allowed inside the pipe, that is instruction fetching stage, fetching from the instruction memory. At the third cycle, instruction 1 is executed by ALU. That means the ALU takes the input 1 is R2, input 2, that is source 2 operand, is R1, and ALU performing the add operation. So then at third cycle, instruction 2 enters into the instruction decode stage. So in the instruction decode stage, okay, at this stage, from the register file, let me simply write as a register file, it is decoding that the source 1 and source 2 operand. Source 1 operand is from R3 register, source to operand from R5 register, and the destination operand is R4 register, that is instruction decode stage. So at cycle 3, instruction 3 allowed inside the pipe, that is fetching the instruction from instruction memory. And the beauty here is, at the fourth stage, instruction 1 is moving to the next stage in the pipe, that is memory access stage. But instruction 2 is supposed to enter into execution stage, but R3 value is not yet updated. So the instruction 2 stops its execution, that we call stalling. So how to stall? By inserting a bubble in the pipe. Inserting a bubble in the pipe. So instruction 2 still in the instruction decode stage only, not moved in the execution stage. So when instruction 2 is in the instruction decode stage in the pipeline, instruction 3 will remain in the instruction fetching stage only. It will not move forward to the next stage in the pipe, because pipe is a one-way direction. So instruction 3 also stalls. So by entering the bubble inside the pipe, the instruction 3 also stalls or stops its execution. So at the fourth cycle, instruction 4 is supposed to enter into the pipe, but the instruction fetching stage is still occupied by instruction 3. So obviously instruction 4 also bubbled. At the fifth cycle, instruction 1 writes the result of R2 plus R1 into R3 register in the first half cycle. So still the write operation is going on. So instruction 2 cannot continue its execution. So in the pipeline, another bubble is inserted. So instruction 2 still in the instruction decode stage. So then instruction 3 still remain in the same stage in the pipeline. So it is simply inserting the bubble, means stopped execution, still in the instruction fetching stage. So obviously instruction 4 will not allow inside the pipe. So that also still not allowed to execute the instruction 4. At the sixth cycle, instruction 2 moves into the execution stage, because by that time instruction 2 will get the source 1 correct value, that is R3 correct value. So at this time, instruction 2 takes 2 inputs by the ALU. Input 1 is R3, that is ready, because which is written at the fifth cycle. Second input is R5. So ALU will get the correct values, source 1, source 2 values that read from these two registers. So instruction 2 moving to the next stage in the pipeline, that is execution stage. So instruction decode stage become idle. So instruction 3 move into instruction decode stage. So at this time, instruction 3 will get the correct value, that is R3, which is written in the fifth stage, and instruction 3 will get the correct value, the R3 and R5 values. So when instruction 3 moved to the next stage in the pipeline, instruction decode stage, instruction 4 allowed inside the pipe, that is instruction memory, fetching from instruction memory. Then at the seventh cycle, Instruction 2 moves to the next stage in the pipe, that is memory access stage. And instruction 3 moves to the execution stage in the pipe. And instruction 4 moves into the instruction decode stage in the pipe. At 8th cycle, instruction 2 completes its execution and writes the value into R4 register. Instruction 3 moves into the next stage in the pipe, that is memory access stage. Instruction 4 enters into the execution stage. At 9th cycle, instruction 3 completes its execution and writes the value R3 plus R5 into R6 register. And instruction 4 enters into the memory access stage. And at the 10th cycle, instruction 4 completes its execution and writes the result into the R7 register. So the same instructions, when there is a read after write hazard, the first solution is by stopping their execution in the pipeline by inserting the bubbles into the pipe. These 4 instructions completed their execution successfully in 10 cycles. So then what is the average cycles per instruction here? Means total 10 cycles over 4 instructions. So that gives almost like how much? 2.4 something. So that is the average cycles per instruction. So this is the first solution that we called stall the pipe. This we call stall the pipe. So this is the first solution, and this is the simplest solution for the data hazards as well as for control hazards also.